This is video number 3 on electric charges and fields. Timestamps are given in the description box. You can watch parts of video if you are running short of time. In this video, I'll talk about electric dipole, how dipole moment vector is defined, how to find electric field along axis of the dipole and on equatorial plane, what will happen when a dipole is placed in external electric field, how to find potential energy of a dipole placed in a uniform electric field. I will discuss 3 conceptual questions. Solve 6 questions from JEE Main PYQs. Finally, I will summarize this video. Electric dipole consists of 2 point charges plus q and minus q separated by a small distance d, which is also represented as 2a. Here there are 2 point charges minus q and plus q separated by a distance d. Dipole moment vector is defined as the charge q into the separation 2a, and the direction is from minus charge to the positive charge. So this arrow shows the direction of the dipole moment vector. Electric fields are present all over the space surrounding the dipole, but in 2 cases it is easy to calculate the electric field. One is along the line joining the 2 charges, there is the dipole axis, and another one is the points on the equatorial plane. So first let's find the electric field along the axis of a dipole. This is a dipole minus q and plus q separated by a distance 2a, and let us find electric field at a point P, which is at a distance r from the center of the dipole. This is the midpoint of the dipole, so the point P is at a distance r from the middle of the dipole. The electric field at point P will be due to the positive charge q and the negative charge minus q. Electric field is force acting on unit positive charge. So electric field due to plus q will be a repulsive force towards left, and electric field due to minus q will be an attractive force towards right. And since this point P is on the left side, it's closer to the positive charge. So the magnitude of electric field due to plus q will be more compared to minus q. So the net electric field at point P will be towards left, and direction of dipole moment vector is from minus q to plus q. That is also towards left. Electric field at point P, which is at a distance r from the center of the dipole, is given as 1 by 4 pi epsilon naught, the charge minus q divided by the distance square. Minus q is at a distance from here to here, it's r, and this distance is half the size of the dipole, which is a. The distance of minus q from the point P is r plus a. So distance square is r plus a square, and electric field due to plus q is q divided by the distance square. Distance of minus q plus q from point P is this much. So that is r minus this distance, which is a. So this distance is r minus a. So electric field due to plus q is q divided by r minus a square. So this can be simplified. In the numerator, r square and a square will cancel. So we'll give 4ar, and q and 2a can be combined as p. Dipole moment vector is defined as the charge into separation. So the electric field expression is 1 by 4 pi epsilon naught 2pr divided by r square minus a square the whole square. And electric field is a vector, and the direction of the electric field at point P is towards left, which is same as the direction of the dipole moment vector P. So if you multiply this by P cap, we'll get the electric field vector, and P cap can be combined with P and written as P vector. Under the dipole approximation, that is at points which are much farther away compared to the size of the dipole, this a square can be neglected. So the expression for electric field will become 1 by 4 pi epsilon naught 2p divided by r cube. Electric field due to dipole goes as 1 by r cube. For a given dipole, this p is fixed. For a point charge, the electric field goes down as 1 by r square. So compared to a point charge, the electric field due to dipole dies down faster. Now let's find electric field on the equatorial plane. Equatorial plane is the plane which is in the middle of this two charges minus q and plus q and perpendicular to the dipole axis. This angle is 90 degrees. So it's symmetrically placed between the two charges. Any point on this equatorial plane will be equidistant from the charges plus q and minus q. The electric field at point P due to plus q will be a repulsive force in this direction, and due to minus q will be an attractive force in this direction. And because of symmetry, these two angles will be same. So the net electric field, the vertical component of plus q which is upwards and vertical component of minus q which is downwards, they will cancel. But the horizontal component which is towards right will add. The electric field at point P, which is at a distance r from the center of the dipole, is 1 by 4 pi epsilon naught the charge divided by the distance square. The distance between q and the point is this one, which is a square plus r square. That is the square of the distance. So distance square is r square plus a square. And we have to take the cos component. This angle is theta. So this angle is also theta. And 2 because one from plus q and another from minus q. And cos theta can be found from this triangle. This side is a, half the size of the dipole. So cos theta is a divided by square root of a square plus r square. So using that, we get the expression for electric field as 1 by 4 pi epsilon naught P divided by r square plus a square is equal to 3 by 2. We have combined Q and 2A as P, the dipole moment vector magnitude. The direction of the electric field is towards right and it is opposite to the direction of the dipole moment vector. So if you multiply this by minus P cap, we'll get the electric field vector, and minus P cap and P can be combined as the vector minus P. Under the dipole approximation, where the distance r is much larger than the size of the dipole, E square can be neglected. So the expression for electric field will become 1 by 4 pi epsilon naught minus P by r cube. So the electric field on the equatorial plane also goes as 1 by r cube. For a given dipole, P is fixed. So for a point charge, electric field goes as 1 by r square. Electric field due to a dipole dies down faster than that. Now let us consider what will happen when a dipole is placed in a uniform electric field. So this is a dipole minus q plus q separated by distance 2a, and the electric field is uniform and it's vertically upwards. So due to this electric field, the positive charge q will experience a force in the direction of the electric field, that is upwards, and minus q in the direction opposite to the electric field, that is downwards. So if we consider dipole as a system, the net force acting on this dipole is QE minus QE, which is 0. So if dipole is considered as a system, the net force acting on it is 0. But this force is acting at two different points. So there could be a torque. So because of this force acting on plus Q, there will be a torque in the anti-clockwise direction. The dipole will rotate about the center point. The mass of both plus Q and minus Q are same. So it will rotate about the symmetry point, which is the midpoint. And this force minus Q will also produce a torque in the anti-clockwise direction. So torque on both plus Q and minus Q are in the same direction. So they'll add to give a net torque. To get the magnitude of the torque, you have to take the force and then multiply with the perpendicular distance of the force from the axis. The axis of rotation is the axis passing through this midpoint and perpendicular to the plane of the paper. So this perpendicular distance is, this length is A. So this perpendicular distance will be A sine theta. So the torque will be Q into A sine theta, and this perpendicular distance is also A sine theta because this is A and this angle is theta. So the total torque will be twice QE A sine theta, and Q and 2A can be combined as P. So torque is P sine theta. So, and the torque direction is anti-clockwise. So the anti-clockwise torque can be represented by a dot vector out of the plane of the paper. The fingers will curl in the direction of the rotation, and the thumb will give the direction of the torque. And direction of P cross E is also out of the plane of the paper. So the vector form of the torque is P cross E. So this is the formula for torque acting on a dipole placed in a uniform electric field. Potential energy of a dipole placed in uniform electric field. This is dipole minus Q plus Q, and the uniform electric field is towards right, and the dipole moment vector is from minus Q to plus Q, which makes an angle theta with the electric field. So because of the electric field, there will be forces on this charge. So there will be a torque on plus Q and minus Q, which are in the same direction. So the electric field will exert a torque in the clockwise direction. So to rotate the dipole through a small angle d theta in this anti-clockwise direction, an external agent has to do work to overcome this torque due to the electric field. That external work done will be torque in d theta. This is analogous to work done in translation motion, which is F dot ds. Rotation motion is torque into d theta. And torque is P cross E, which is PE sin theta, where theta is the angle between P and E. So this work done by the external agent will go in increasing the potential energy of the dipole. So increase in potential energy is dW. So suppose if we rotate this dipole from this position theta to the vertical position, which is theta 90 degrees, then the total work done will be integral of this dW from theta to 90 degrees. That work done will go in increasing the potential energy of the system. So final potential energy corresponds to 90-degree position minus initial potential energy, that is theta position. Integration of cos sin theta will give minus cos theta, and putting the limits we get P cos theta, and that can be written as P dot E, where theta is the angle between P and E vectors. If we choose potential energy of the dipole to be 0 at theta equal to 90 degrees, that is when the dipole axis is perpendicular to the electric field, that is U90 is 0, then the above equation becomes, for potential energy we can choose a convenient reference point where we can assume that the potential energy is 0. So here we will assume that the dipole position corresponding to 90 degrees as corresponding to 0 potential energy. So with that convention, we get the potential energy for theta position is minus P dot E. So this is the formula for potential energy of a dipole placed in external uniform electric field. Let's consider this question. A dipole is in equilibrium if force and torque on it is 0. For a point mass, we can say it's in equilibrium if the net force acting on it is 0. But for an extended body to be in equilibrium, both the net force and the net torque has to be 0. Dipole in extended body, because it has got two masses separated by a distance 2a. So both torque and force has to be 0 for it to be in equilibrium. For a dipole in uniform electric field, what are the equilibrium coefficients? What are the corresponding values of theta? And is it stable or unstable equilibrium? You can pause and attempt this question. The force acting on the dipole when the electric field is uniform is 0, because force acting on the positive charge will be along the direction of electric field QE, and on the negative charge will be minus QE in the direction opposite to the electric field. So the net force will be two equal and opposite forces, so it will be 0. So the net force is always 0 when the electric field is uniform. And the expression for torque is given as P cross E for uniform electric field, and P cross E is P into sine theta, where theta is the angle between the dipole moment vector and the electric field. And sine theta can be 0 for theta being 0 or 180 degrees. So two positions are possible where the net torque is 0. So there are two equivalent positions corresponding to P and E being parallel, that is for theta equal to 0, and anti-parallel where theta is 180 degrees. Now we have to find whether this equilibrium is a stable equilibrium position or unstable equilibrium position. At theta equal to 0, the positive charge will be plus Q will be here of the dipole and minus Q will be here. In that case, if we try to give a small perturbation or a rotation in this anti-clockwise direction, there will be a torque acting on this dipole in the clockwise direction because of this force, and this minus q also experience a force torque in the clockwise direction. So if you try to displace it by a small angle in the anti-clockwise direction, this restoring torque will bring it back to the equilibrium position. So similarly, if I try to displace this in the clockwise direction, the torque will act in the anti-clockwise direction and bring it back to the original position. So theta equal to 0 corresponds to stable equilibrium position. But 180-degree, the positive charge will be here, plus q, and minus q will be here. So at this position, if I try to displace it a little bit on the clockwise direction, the torque acting on the dipole is in the clockwise direction. So it will take it away from the original position. Similarly, if I try to displace this dipole a little bit on the anti-clockwise direction, there will be a torque in this direction that will take it away from the equilibrium position. So theta equal to 180 degrees corresponds to unstable equilibrium position. Let's consider the next question. Is torque acting on a dipole placed in uniform electric field constant with respect to the position theta? What about angular acceleration? You can pause and attempt this question. Torque acting on a dipole is given as P cross E. It's in a uniform electric field, which is P sine theta, and the direction is, in this case, P is this direction, so it is into the plane of paper. So depending on the position of the dipole, theta will change, so the magnitude of the torque will change. So torque is not uniform, it depends on the position, that is on theta. And this torque equal to I into alpha. From this we get alpha as P sine theta by I. I is moment of inertia about the rotation axis, and the rotation axis is point middle of the dipole and perpendicular to the plane of the paper. So moment of inertia about this axis is ma square, where m is mass of the charge, into twice, one from plus q and another from minus q. So this is a constant. So even the angular acceleration depends on the position theta. So angular acceleration is also non-uniform and it is very sinusoidally with respect to theta. This is the next question. Get the expression for potential energy of a dipole placed in uniform electric field as a function of theta. Find minimum and maximum potential energy locations. Does this correspond to stable and unstable equilibrium positions? From potential energy consideration, a stable equilibrium position will correspond to potential energy being minimum, and unstable equilibrium position will correspond to potential energy being maximum. You can pause and attempt this question. Potential energy is given as minus P dot E, which is minus P cos theta, where theta is the angle between the vectors P and E. So this changes with respect to theta, and cos theta varies from minus 1 to plus 1. So for the potential energy to be maximum, cos theta should be minus 1. So that corresponds to 180 degrees. And the maximum value is P into E. And for it to be minimum, cos theta should be plus 1. That corresponds to theta equal to 0. So minimum value corresponds to 0 degrees and its value is minus P. And maximum potential energy corresponds to unstable equilibrium position, and minimum potential energy corresponds to stable equilibrium position. This is consistent with the result we got by dynamical considerations here. This is a question from JEE Main 2019. Charges minus q and plus q are located at A and B respectively, constituting an electric dipole. The distance AB equal to 2A, O is midpoint of the dipole, and OP is perpendicular to AB. A charge q is placed at P, where OP is Y and Y is much larger compared to 2A. The charge q experiences an electrostatic force F. If q is now moved along the equatorial line to P prime, such that OP prime is Y by 3, force on q will be close to Y by 3 is also much greater than 2A. You can pause and attempt this question. So initially the charge q is at location P, which is at a distance Y on the equatorial line. So because of this, let's assume capital Q is positive charge. That does not affect the answer. So because of this plus Q, there will be a repulsive force in this direction. And because this minus Q, there will be an attractive force. This point P is on the equatorial line. So it is symmetrically placed between the two charges. So if this force makes an angle theta with the y-axis, this force will also make an angle theta with the y-axis. So the net force acting at point P is sum of these two forces. The vertical component will cancel, one up and one down. The horizontal component will be towards left and it will add. So the net force acting at point P is 2F1 sine theta. F1 is the magnitude of this force, which is given by Coulomb's law, which is K. K is 1 by 4 pi epsilon into product of the charges Q into Q divided by the distance square. The distance between P and B is this square plus this square, square of the distance. So A square plus Y square. And sine theta is this opposite side, E divided by hypotenuse, that is square root of A square plus Y square. So under the approximation, they are given that Y is much larger compared to A in the question. So we can neglect A square compared to Y square here and here. So Y square and Y will combine to give YQ. So force is this expression. When the charge moves to P prime, the net force acting on it will be 2F2 sine theta 2. The F2 is the magnitude of the Coulomb force between these two. And the angle will be different. That will be theta 2. So F2 is product of the charges Q and Q divided by the distance square, that is A square plus Y2 square. And sine theta 2 will be A2 A divided by square root of A2 A square plus Y2 square. And Y2 is Y by 3. So using that we get the force as Y by 3 cube. So 3 cube will go in the numerator. And this is FP. So the force is going up by 27 times. So correct option is option D. This answer also can be got straight away from using the electric field expression for dipole. Electric field of a dipole along the equilibrium goes as 1 by distance cube. So when the distance is being reduced 3 times, the electric field will go up 3 cube times. So the force on a charge will also go up by 3 cube times. So from that we can straight away get the answer as 27 times. This is the next question. This is also from JEE Main 2020. An electric dipole of moment P equal to minus I cap minus 3J cap plus 2K cap into 10 raised to minus 29 coulomb meter is at origin 0, 0, 0. The electric field due to this dipole at the location R equal to I cap plus 3J cap plus 5K cap is parallel to. Note that R dot P is 0. They are given this hint. You can pause and attempt this question. R dot P here is minus 1 into 1, that is minus 1, and minus 3 into plus 3, minus 9, 2 into 5, 10. So R dot P is 0. That means that the vector R and P are perpendicular. So you have to find the electric field at the location where it is perpendicular to the dipole moment vector P. So this corresponds to points on the equatorial plane. Electric field due to a dipole, this is the picture. Electric field lines will start from plus Q and it will end at minus Q. And the origin of the coordinate system is at the center of the dipole because the dipole is placed at the origin. So the point where The position vector is perpendicular to the P vector corresponds to the points on the equatorial plane. So the point is in the equatorial plane, and on the equatorial plane, the electric field direction is here towards right, and the P vector is from minus q to plus q, it's towards left. So the direction of the electric field is opposite to the direction of the dipole moment vector. So E direction is opposite to dipole moment vector, that is anti-parallel to dipole moment vector. So direction of electric field is negative of the direction of the dipole moment vector. Direction of dipole moment vector is -1, -3, +2. So direction of electric field will be 1, 3, -2. 1, 3, -2. So correct option is option 1. This is the next question. A point dipole P equal to minus P naught x cap is kept at the origin. The potential electric field due to this dipole on y-axis at a distance d are respectively, take V equal to 0 at infinity. You can pause and attempt this question. So the dipole is along the x-axis and is kept at the origin, and we have to find electric field on the y-axis, that is on the equatorial plane. Potential difference between 2 points is given as minus E dot dr, and if E and dr are perpendicular, then the potential difference between the 2 points will be 0. So since we have to find the electric field on the equatorial plane, and they have given the electric field at infinity is 0, and the work done in moving from any point on the equatorial plane is 0 because we are moving perpendicular to the electric field. So the work done in moving from, say, this point to this point is 0 because we are moving in a direction perpendicular to the electric field at all points. So whatever is the potential at this point will be same as potential at this point, same as potential at this point, this point. So all the points in the equatorial line or equatorial plane will be at the same potential, and potential at infinity is 0 that they are given. So the same 0 potential will continue throughout. Another way of getting this answer is any point of the equatorial plane is equidistant from the positive charge and the negative charge. So potential due to positive charge will be the charge q by the distance, and potential due to the negative charge will be minus q divided by the distance. Distance is same because in the equatorial plane. So the net potential will be 0. So potential for the points will be 0. So V is 0. Electric field, we can use the standard formula, which is 1 by 4 pi minus P by RQ. And here R is D. So the correct option is option D. This is the next question. Electric field of 1000 volt per meter is applied to an electric dipole at an angle 45 degrees. The value of electric dipole moment is 10 raised to minus 29 coulomb meter. What is the percentage of the dipole? You can pause and attempt this question. This is a simple question. We just have to use the formula for potential A for dipole in uniform electric field, which is minus P dot E. And the angle between P and E they are given as 45 degrees. So it is P into E into cos theta. P is 10 raised to minus 29. Electric field is 1000. And cos angle is 1 by root 2. Cos 45 is 1 by root 2. So 100 we can combine with this one to give 10 raised to minus 27. And 10 by root 2 is 5 root 2, which is 5 into 1.414. 5 into 1 is 5. 5 into 0.4 is 2. 5 into 0.01 is 0.05. So it's approximately minus 7.05 into 10 raised to minus 27. Correct option is option 2. This is the next question. Determine the electric dipole moment of the system of three charges placed on vertices of an equilateral triangle, as shown in figure. You can pause and attempt this question. So the charge minus q placed here can be thought of as made up of two charges minus q and minus q. So one minus q and this plus q will form a dipole, and second minus q and this plus q will form another dipole. and dipole is a vector. So we have one dipole like this and one dipole like this. So the net dipole moment will be sum of these two vectors. This is an equilateral triangle, so this total angle is 60. So the angle made by the dipole with the vertical will be 30 degrees. So the sum of these two dipoles will be the vertical component, the horizontal component will cancel. So it's p cos theta into 2. And cos 30 is root 3 by 2. And p is the charge into distance, that is q into L. And the direction is downwards, which is minus j cap. So it will simplify to ql into root 3. Direction is minus j cap. Correct option is option 3. This is the next question. An electric dipole has a fixed dipole moment p, which makes an angle theta with respect to the x-axis. When subject to an electric field E1 equal to EI cap, it experiences a torque T1 equal to tau k cap. When subject to another electric field E2, which is equal to root 3 E1 j cap, it experiences a torque T2, which is equal to minus T1. The angle theta is. You can pause and attempt this question. The torque on a dipole based on uniform electric field is given as P cross E. The dipole moment makes an angle theta with the x-axis. So in vector form, P is P cos theta I cap, P sin theta j cap. And cross product we can write in terms of determinant. So it's ijk, and P vector is P cos theta P sin theta 0, and P can be taken out commonly, and electric field is E I cap 0 0. And in the second case, the electric field is root 3 E j cap. So this can be simplified. So it will be k cap into 0 minus E sin theta. So the torque is this one. And in the second case, the torque will be k cap into cos theta into root 3 E. And the torque in the first case is tau k, which they are given in the question. And in the second case, it will be minus tau k. So combining these two, we get E sin theta equal to root 3 into E cos theta. So that means tan theta is root 3. That corresponds to theta equal to 60 degrees. Correct option is option C. To summarize, dipole moment vector is defined as the charge q, the separation between them 2a, and the direction is from negative charge minus q to positive charge plus q. Electric field along axis of a dipole is given as 1 by 4 pi epsilon naught into 2p by r cube for distances which are much larger compared to the size of the dipole. And electric field along the equatorial plane is 1 by 4 pi epsilon naught minus p divided by r cube. Again, under the same dipole approximation where the distance is much larger compared to the size of the dipole. So the way to remember this formula is, for a point charge, the electric field will go as 1 by r square. For a dipole, it will go as 1 by r cube. And it depends on the vector p. And field along the dipole axis is more by a factor 2. And direction we can get from simple physical picture. So along the axis, it will be same as p. On the equatorial plane, the electric field lines will go from plus q to minus q. So using that picture, we can figure out that the direction of electric field will be minus p. Torque of acting on a dipole placed in a uniform electric field is given as P cross E, and potential energy of a dipole placed in uniform electric field is given as minus P dot E. So this will correspond to the potential energy being 0 when P and E are perpendicular. That is when the angle between the dipole moment vector and electric field vector is 90 degrees. I also take doubt solving sessions from physics and math subjects of JEE and NEET. If you are interested, you can contact me. This is my WhatsApp number. Fees is nominal and first class is free. Description box has got links and timestamps. You can watch parts of video that you will find interesting.